Now then we come back to the equations. So from the graphs we learn the cases, counterexamples where your estimator, your extremum estimator does not converge to the true parameter. So in this case, mathematically, the conditions to guarantee the consistency there are two conditions. So first, assume that the true parameter is a maximum of the true criterion function, and your estimator is obtained by maximizing a estimated criterion function. For your estimator to converge in probability to the true parameter, you need to have these two conditions. First, theta 0 is a clean maximum of Q0 criterion function. The clean maximum is a mathematical term. I expressed a mathematical term in this way. If you are good at epsilon delta method, you can find theorem 2.1 in Ewing-McFadden paper. I will just do it in this way. So this is not a clean minimum because there is a very close point. There is another point which approaches to the minimum, nearly approaches to the minimum. So in the limit, it will be the same, but fortunately the limit is empty. The point is discontinuous, so it is not the minimum, but the minimum is here. In this case, your parameter is not a clean maximum. So, and second, uniform convergence. Q hat n must be uniformly converging in probability to the true criterion function. So uniform convergence rules out this or this case. So these two cases are not uniformly converging. So it is too slow here, and it is slow as you go to the infinity. So to prevent those kind of cases, you need to have uniform convergence. These conditions are called identification condition and uniform convergence condition. Uniform convergence is literally the uniform convergence we learned earlier, and mathematical statement of condition 1, identification condition, can be found in the reference, and there is simply, it means there is no closed alternative. And I'm not going to prove the consistency because its proof is not, I don't think it's not important. It is purely application of analysis, epsilon delta method, and in many cases consistency is quite obvious. Consistency, though you know the result. If it is consistent, that's consistent. So the proof, I don't think proof is important, but later we are going to prove there are more things to prove. So I will skip this. I will not show you how to prove that. If you're interested, read this paper. The proof is like short. It's like 2 or 3 lines. So if you are good at epsilon delta method, it's worth reading it. And then the problem here is, so there are two conditions which look simple, but it is not convenient to see if your model satisfies these conditions or not. So there are some sufficient conditions for the identification condition. By the way, uniform convergence condition was discussed earlier. Where was this one? So we learned lemma 7 tells you what is the sufficient conditions for uniform convergence. So you may check uniform convergence using these conditions, and also to check now. So uniform convergence is uniform convergence condition can be split into so easier conditions as before, and now ID condition, identification condition, can be split into easier conditions like this. First, it is obvious the function must be uniquely maximized at a point. It is obvious, it has to be unique maximum. So even this case, theta 0 is unique because theta 1 is not a maximum. So it is unique. So it is easy. It is satisfied in many cases. Or in practice, it means that your maximum satisfies the first order condition and the second order condition. So it is related to the second order condition. And second condition is the compactness. The parameter must belong to a parameter space, capital theta, which is a compact set. Compact set is closed and bounded. It must be closed. So so it should include the endpoint, and it should be bounded. It should not include the infinity. And third, the function must be continuous almost surely. Continuous in theta almost surely, and like L is the log likelihood function. The log likelihood function is continuous in theta almost surely. So then combining these, especially compactness and continuity, are important conditions to guarantee a unique maximum. So if you have taken mathematical analysis, usually maximization theory is based on these two assumptions. So these two guarantee that the maximum is clean. There is no closed alternative. So then, as a result, another sufficient condition is to show that the criterion function is globally strictly concave. Globally strictly concave means it's so it's exactly look like this. So there is only one unique maximum, which is really nice, but it is in many cases it is more difficult to verify. So these conditions are more commonly used in the literature. So these are easier to verify than this. And so combining this and the uniform low large numbers, this lemma 7 and lemma 11, combining them is lemma 11, lemma 7, we have these four assumptions. So some sufficient conditions have overlap, like continuity is included in both lemma 7 and 11. So in the end, you only need to check four assumptions to verify these two assumptions, and in the end to verify consistency. So your estimator is consistent under these four assumptions: unique maximum, compact, continuity, and boundedness of the function, uniform boundedness. And application to OLS. To show the consistency of OLS, by the way, maybe you have learned the consistency of the OLS in Econometrics 1, and there are many different ways to prove the consistency. But here, if you want to use this general theorem, you need to just check four of them. So first, unique maximum of that second order condition is easily verified. And assume that beta belongs to a compact set. So simply assume that there is a large number C, which is, and assume that the parameter is smaller than the number, plus minus C. And then, isn't it the problem? And usually it's not a big problem because you may choose, so anyhow, you are going to use a computer, and there must be like a limit in the computer program, like memory maximum, something like that. So the maximum possible number a computer can recognize. You can think this bound as this kind of number. And assumption 3, continuity, which is obvious because the functional form is clear, it's quadratic function, so obviously continuous. And condition 4, you need to assume that the parameter is finite, and if the expectations are finite for the random variables, then you can show that the supremum is also finite, so uniformly bounded. So everything is bounded, then the log likelihood function, the squared residual, is also bounded. See, y is bounded, y is smaller than something, x is smaller than something, beta is smaller than something, then combined all of them, it must be smaller than something. So you just need to find what is that something. Okay, in this video we studied consistency, which is brief and looks easy. And in the next video we are going to start asymptotic normality, which is much more difficult. So see you there.